So yeah, I guess we can get started. Welcome to my fourth lecture for quantitative finance. I just would like to recap what we did so far. So we're using the linear regression model to estimate our betas here for different stocks in our stock universe. And we use the OLS point estimator for determining the sensitivities against the market factor, which was our X matrix in our simple first example. Yeah. So I disregard now from the index I here that we usually have, that we should use here, because in order to denote the excess returns of stock I, in our framework, the Y vector denotes the excess returns of each stock. And there's no index on the X matrix because we use always the same regressor matrix here. And also here I will also disregard the I index for the corresponding beta estimate, for illustrative purposes here. So based upon our linear regression model, we also know that we can, from this it follows that the error term, the U, is simply defined as the excess returns minus the beta loading times the market factor in matrix notation. Yeah? So we usually use in this course matrix notation. So what we also said, okay, the market factor we treat it as not random. So the only random component is actually our error factor here. Yeah. This error vector here is actually given, it's the t/1 vector. Yeah. And in the same manner, of course, our Y vector is t/1. Our X matrix has also the dimension t/1 in case we just use the excess returns of the market factor. If we include the intercept term, then we have a t/2 matrix. If we would use the Farmer and French 5-factor model and add the intercept term, then we would have a t/6 matrix. Yeah? Depending on the column rank of our regressor matrix, which is the factor matrix in our context, this determines the dimension of the beta vector, yeah? Where we actually store the point estimates, the sensitivities against our risk factors for the stock Y. So in our framework, because U is random, and U denotes in our framework, in our context, the firm-specific part of the excess returns, the part of the excess returns of stock Y that is not explained by the systematic risk exposure against the market factor. It's the idiosyncratic or the firm-specific part of the excess returns. Yeah? So because this guy here is random, X is not random right now, so therefore Y is random as well. Yeah? Each stock return for each point in time is the simple linear combination of the error term. Yeah, I think that's obvious from the equation, right? So Y depends on U, and U is random, therefore Y is random as well. What we assume also in our standard OLS framework that each U is normally distributed. Yeah? Each U is normally distributed. It has the same mean with a 0 and the same standard deviation or the same variance with this sigma squared. So, and what we also see here, because Y is random, beta hat, our point estimator, must be random as well, because it's a linear combination of our Y vector. So it's a linear combination of t random variables, because Y is t/1, like this guy here, and each of these random variables is normally distributed. So it's a linear combination of a normally distributed random variable. And what we know from statistics class is that a linear combination of a normally distributed random variable is normally distributed as well. So therefore, this guy here has also a distribution, or point estimator, and it's normally distributed as well. So once we have estimated our beta here, we can plug it into this equation here, and what we get is the estimated residuals. What we get is the estimated residuals. It's noted as y, as u hat, which is given by y minus x times beta hat. Yeah? And this is actually, we need those as well later on. So once we upload the data matrices, like the y vector and the x matrix, like our market vector, then we can immediately estimate the market sensitivity. And once we have done that, we know also the estimated residuals. So everything is given by the data. You just need to upload it. So if we have two random variables, let's say x1 and x2, which are, for instance, our intercept terms or whatever, so and we assume they are 0. But what's the variance of two random variables that sum up to 0? Yeah. So we have to think about, and we are talking about this also in the RFM course actually. So the variance of this linear combination of two random variables is the variance of the first guy plus 2 times the covariance of these two random variables, like x1 and x2, plus the variance of the second guy. So if we define a random variable as x1 and x2, let's say our lambda is x1 plus x2, then the corresponding variance of this random variable that we defined, so the corresponding variance of lambda is given by this equation here. Yeah. So whenever we are dealing with a test statistic, we have to standardize it. I mean, intuitively speaking, we have to standardize it by its standard deviation. If we use just the sum of random variables, and we remember from the chi-square test, we usually use the sum of squared normally distributed random variables. Yeah. So what we would do then is we would take this equation here. If we would take just the sum of them itself, we would need to use the square root, like the standard deviation of that guy, in order to standardize the random variable or test statistic. But in case we use the squared ones, we would take the term as it is here. Yeah. So the problem is in the GRS test that we have, if we have like 14 test assets, like in our simple example, we have many of these covariance terms. Yeah. So that's why we would be supposed to implement this multivariate test, this GRS test, that takes into account these covariance terms here. Because the assets are correlated usually, and therefore the intercept terms that are random variables and that are also dependent on the assets, they are correlated as well. So that's why we have to use this GRS test, that takes into account the covariances. So that was the reason for why we went through it in this GRS course. But for now, in this simple example here, what we will go through very soon, so we will assume that these guys here are 0, that they don't matter. Yeah? So we assume the assets are uncorrelated. And our decision, so what we will do is, we will say, okay, if more than 5% of our assets have significant alphas, then we would conclude, okay, the CAPM cannot price our test assets correctly. This is what we will, for simplicity, assume here. This is, of course, not correct, because we know already the errors, the assets are correlated, and so are the intercept terms. The alphas are also correlated, so actually we cannot do it like that. But for simplicity, we will assume it for this exercise 3, what we will go through very soon. So just that you have in mind the link between what we do here and between what we did in the RFS, in the RFM course. Yeah. So actually, we have to run the GRS test, which is also not so difficult to implement in Matlab, of course. Once you just have to code it once, but actually we have to take into account, or we should take into account, that the intercept terms are correlated. Yeah. Because think about it, we have 14 test assets, and we have 14 intercepts. Yeah? And the GRS test says, okay, that all the alphas, all the intercept terms are different. Under the null hypothesis, they are different. They are equal with 0. So we have our test statistic has 14 squared random variables that are normally distributed, and we would be supposed to standardize them by this expression here, which becomes huge, yeah, because of the covariance terms that are part of that denominator. Yeah, but for now we just assume we don't have to take into account the covariance terms. So when we use an asset pricing model like the CAPM or the Farman-French 3-factor or 5-factor model or whatever, and we use our OLS formula and we get our point estimates, we want to know if our point estimates are significant. Yeah? We want to know if they actually, we remember from the RFM course, we were talking about, okay, if the loading is positive, for instance, against the profitability factor, we would conclude, okay, this portfolio is invested in stocks that have a high profitability. Or if the sensitivity against the value factor would be negative, we said, okay, this portfolio is exposed to growth stocks because it co-moves with the short leg of the value strategy, right? But if the t-statistic would be, let's say we remember the normal distribution, and we have our critical values of 1.96 and minus 1.96. And let's say we have a point estimate, the point estimate is negative, but the t-statistic is something like, I don't know, here, minus 1.3 or something. Actually, we cannot say, or in this case, we could not conclude that this portfolio is exposed to growth stocks, because statistically, the exposure is not different from 0. Which implies that this portfolio would be equally invested in growth and value stocks. We could not say it's somehow exposed to one of these sides, because statistically, the point estimate would be not different from 0. And the same logic applies to all the other factors or to all the other exposures. So in order to make a conclusion, in order to come to a conclusion, we have to determine what is the t-statistic of each of these point estimates, of our parameter estimates, of our asset pricing model. Only then we can make strong conclusions. So if you want to test the intercept terms, the same logic applies here. So we have to determine what is the t-statistic of the intercept terms in order to determine if the asset pricing model can price our test assets or not. So we know already how to get our point estimates. And last time we were also discussing what happens if actually our model is wrong. Yeah. But now we have to discuss, okay, we know how to estimate the point estimates, but how do we get the t-statistics? And how would we get it if we have, like, let's say 10,000 assets? So it's easy to do in Matlab, but we have to understand first how the system works. So for instance, is the distribution of our estimated beta, let's say this is beta hat 1 of asset I. Yeah. The distribution can look like this. If the sigma is very high, it's noisy, so most likely this point estimate would be not different from 0. Or does it look like this? That's a difference, obviously. So this is now what we are interested in. This is now what we want to figure out now. What's the distribution of the point estimate in order to get the t-statistic? So once again, so the question is, what's the variance of our point estimates? And I think this blue pen here doesn't work anymore, so I will take the black one. So what's the variance of our point estimator, beta hat? Yeah. Again, we know from statistics class what we have to do is we take the estimated beta minus the expectation times, and we have to, now I have to close. So we take the point estimate that we minus the expected point estimate times itself transposed. No, wait, this has to be transposed, right? No, it's k by 1, k by 1, 1 by k. Yeah, this has to be transposed, that's correct. So what we would get is a n by n matrix here. Yeah, it's n by 1 times n by 1 transpose is 1 by n, so what comes out here is the n by n matrix. So what we would get is the n by n matrix, because if we have n regressors in our regressor matrix X. Yeah. So how do we get this expression here? That's not the question. And now we remember from, I think it was the first lecture, so the point of departure is again our standard formula here, and then we can plug in for y what it is. Yeah, y is x times beta plus u. So now we plug it in. So now we can multiply it out. I think we did it last time as well. So what we get here is x prime x inverted times x prime x. So what we get here is the identity matrix, because we multiply a matrix product with itself inverted. So what we would get here is the identity matrix. Identity matrix times beta, which is simply beta. And we get this guy here, this expression, times the error vector plus x prime x inverted times x prime u. So now we have our expression already, right? So here's our beta hat. Here's our beta. Now we bring this guy here on the other side of the equation. So what we get is beta hat minus beta is obviously equal with x prime x inverted x prime u. Yeah? It's obvious, right? So what we do now is we plug in this guy that we now calculated into this equation here for our variance. Yeah. So the variance of beta hat is then given by the expectation of x prime x inverted x prime u times itself transposed. We have to transpose this expression now here. So what happens if we transpose a matrix product? So what is on the right hand side gets transposed and appears on the left hand side. So the order changes if we transpose it, okay? We know this from matrix, okay? From matrix algebra. So if we have matrix product A times B transposed is equal with B transposed A transposed. A simple rule. So we have to transpose this guy here. And the second guy is the second element here, the second last guy, and the transposition sign disappears. So because we know also A transposed is A. Yeah. So and then what we also know, A transposed inverted is the same as A inverted transposed. These are simple rules from linear algebra. So we have to take it times x prime x inverted then here. Yeah. So this is our covariance matrix of our point estimator beta hat. Yeah. And we can, once we know what it is, we can actually now already plug it into Matlab and we would get something here. You know, and what we would be supposed to do then is we would use here the estimated u vectors. But we can simplify it. Yeah. According to if our assumptions are true, yeah, we can simplify this expression here. So what's random here? What's the random part here? Yeah. So the random part is this u, right? Because our regression matrix here, we assume that this is not random. Yeah. It's strictly exogenous given. So we can move the expectation operator in the parentheses because only this is random here. And what we get is we can now simplify this expression. Let's move it in to the parentheses. So what we get is here then times the expectation of u times u prime. So u is a t by 1 vector times itself transposed is 1 by t. So the expectation of u times u prime is a t by t matrix. What we have here is a t by t matrix, which looks like that. So u1 so if we multiply this guy here with itself transposed, what's the first element? It's u1 times itself. So it's u1 times u1 or u1 squared. What's the second element? It's u1 times u2. u1 times u2. The third element, of course, u1 times u3, and so on, until we end up with u1 times ut. This matrix is symmetric. So on the main diagonal, we have all these guys here squared times itself, or squared. Yeah? So the last guy here is ut times ut. It's a covariance matrix of our errors, of our residuals. And this covariance matrix is symmetric. So what we have here, this element, u1 times u2, it appears here as well, u2 times u1, and it's the same element. Doesn't matter. The order doesn't matter here, but it's the same element. So everything that we have here above the main diagonal appears also below the main diagonal. Yeah. These are the same elements. That's a typical property of the covariance matrix. It's symmetric. It's a T by T matrix. So what is these guys here on the main diagonal? u1 times u1, what is that? What's the expectation of u1, because we have here the expectation operator. What's the expectation of u1 times u1? Yeah. So according to our assumption, to our OLS assumptions, all of these guys have the same distribution, with expectation of 0 and variance of sigma squared, right? So we can rewrite it. So if we move the expectation operator, we can move it here in. If we take the expectation, for instance, of this first guy here, expectation of u1 times u1, what is that? Okay, we can write it as expectation from u1 minus the expectation from u1 in parentheses times u1 minus the expectation of u1. Yeah? The expectation of u1 is, according to our assumption, 0. So this guy here is 0. This as well. And what's remaining is the expectation of u1 times u1. And this is, according to our definition, the variance of u1. And in the same manner, this is the variance of u2. And the last guy here on the main diagonal is the variance of ut. According to our OLS assumptions, the variance of all of these guys is the same. So what happens on the main diagonal, every element on the main diagonal is sigma squared. So we can rewrite it now, simplify it. Sigma squared on the main diagonal. So what's the expectation of u1 times u2? We do now the same trick. It's the expectation of u1 minus the expectation of u1 times u2 minus the expectation of u2. This is how we could rewrite it. Yeah? The expectation of u1 times u2. We can rewrite it like that because the expectation of each random variable is 0. Yeah? We have just basically expanded the equation. So this is 0, this is 0, this is equivalent. So this is the covariance. This is the formula for the covariance of u1 and u2. And according to our OLS assumptions, the covariance between these errors is 0. Does it make sense? Yes, it makes sense. Think about the covariance would be not 0. What does that mean? If let's say the covariance between the first and the second element is larger than 0, So what we have then going on in our system is a sort of autocorrelation. This would mean that if the firm-specific component of the egress return in period 1 would be high, it's likely to be high in the next period as well. Then we could trade on it. It would be a huge indication or a clear indication of market efficiency. So people would trade on it, and it should disappear again. So because the correlation or the covariance between our errors here is according to our OLS assumption 0, yeah, everything here above in the main diagonal is 0. Zeros everywhere else. Because the sigma squared is the same, we can move it outside the matrix, and what remains is a main diagonal with 1, with ones. So let's move sigma squared out. What we get is on the main diagonal just ones, and that's the identity matrix of dimension t times t. That's what we have here in the middle of our matrix. It's the identity matrix and sigma squared. So now let's move sigma squared outside here. And this guy here, obviously, is the identity matrix, what remains, because the expectation of the identity matrix is the identity matrix. And the identity matrix doesn't change anything. Yeah? We know from matrix algebra all that stuff. A matrix A times the identity matrix is A. Yeah? And if we have a matrix product, let's say A times B, and in the middle we have the identity matrix, it's A times B. Obviously. Yeah? So this guy doesn't change anything here, so we can remove it. So what remains here? It's x prime x inverted times x prime x times the same expression again on the right hand side. So, but x prime x inverted times x prime x, it's the same matrix product times itself, but on the one hand it's inverted. So what remains here is the identity matrix as well. Yeah? That's the identity matrix. Matrix A inverted times itself is the identity matrix. If we define A as x prime x, it's the identity matrix. Yeah? So we can take this guy here away as well, because the identity matrix, it's the identity matrix. So what remains is x prime x inverted. Yeah? So it's sigma squared x prime x inverted. And we know this guy here is the n by n matrix. This guy here we know from the data. We can estimate as we did it like in the beginning of the lecture, right? So we can easily estimate this guy here as the error vector transposed times itself divided by number of observations minus n. This guy here we can estimate. It's then the estimated sigma square, and this is then the estimated variance. And this guy here we get from the data. It's our data matrix, it's our regression matrix that we uploaded already in Matlab. Yeah? That's it. So all the expression here, this is a number here. Our sigma square hat is this is just a number. Yeah, it's a t by 1 vector transposes 1 by t times t by 1. It's 1 by 1 divided by t minus n. This is a number here. This is just a scalar. And what we have here is the n by n matrix. So in our CAPM case, if we include an intercept term, yeah, we have two regressors, n is 2. This guy here, the whole expression is a 2 by 2 matrix. If you multiply it out, what we would get is a 2 by 2 matrix, which looks something like that. Let's say x1. And I'm left-hand writing, so that's why my handwriting style is a little bit fuzzy, I would say. So don't get too excited here. So in our CAPM case, if we have two regressors, this whole expression here, our covariance matrix of our betas, looks like that. Yeah? It's a 2 by 2 matrix. And the first element, this guy here, x11, would be then the variance of the alpha, of the intercept. Yeah? Let's remember what we actually have here. So in our CAPM case, if we include the intercept term, and this is actually what we also do in the third exercise here, yeah, we have a vector of 1s in our regressor matrix, which is first, and then we have the excess returns of the market vector in the second column. Excess return of the market vector. So that's a t by 2 matrix. Yeah? So this guy transposed times itself inverted, yeah, times sigma hat squared. So everything is a 2 by 2 matrix. Yeah? So, and the first element here is the corresponding variance of what is here in the first column of our X matrix. The second element on the main diagonal is the variance of what is here in the second column of our regressor matrix. If we would have the Farmer and Friends 3-factor model, and you would add here the size factor and the H and L factor, the value factor, then we would have a t by 4 matrix. So our covariance matrix here of the point estimator would be 4 by 4. And the third element on the main diagonal would be the variance of the size factor. And the last element on the main diagonal would be the variance of the value factor. Same logic. On the main diagonal are the important things that we need to grab. So what's then the t statistic? So we have estimated, so we have our point estimate. Yeah? We have already done that. Let's say our beta 1, and we have also estimated the covariance matrix here. Our corresponding t statistic, for example, for the sensitivity against the market factor would be then, yeah, we grab the second element, or the corresponding element from the beta vector, which is the second element here, because this gives us the sensitivity against the market factor, and let's denote it as beta hat 1. Maybe it's like, I don't know, let's say 0.7. And we divide it by the square root of x22, of this guy here, of the square root of the second element from this covariance matrix here. So that's the t statistic, the t stat. So the t statistic of the alpha would be accordingly the square root of the first element here, which is x11. Yeah. So we take the corresponding point estimate, which is first here in our beta vector, which is corresponding to the intercept term, and we divide it by the corresponding element here in the covariance matrix, which is the first one here, in the same order. So what's this guy then here? X12. It's the covariance between the alpha and the beta. And this is the same thing here. It's the covariance between the beta and the alpha. So these values here are the same. We usually do not interpret these guys. There may be some research questions where you might need it, but we don't need it at least. But think about if we have a huge system, like we did in the RFM course. Yeah, we have a multiple equation system, yeah, and then we would like to implement the DRS test. So we have our beta vector. If we have, for instance, like let's say 10 assets, and we have 2 point estimates here. Each asset, they have the alpha and the beta. So we have 2 point estimates times 10. We have 20. Yeah, our point estimator would have 20 elements, and the covariance matrix here would be 20 by 20. And what we would then have here are also all the covariances between all of the estimated parameters. And then we would grab, basically, this is what the DRS test is then doing. It would grab the covariances of all the alphas into the test statistic. And that's why we would need the whole estimate of the covariance matrix here. Yeah. So the important thing is, in our case, is things on the main diagonal. Yeah. Is it clear to everybody? And think about now, we can only do that. This formula is only valid if our assumptions are true. If there's no correlation going on in the residuals, if the errors have an average, an expectation of 0, and so on and so forth. And if all the errors have the same variance across time. Yeah. So we will see later on what happens if this is not true. Yeah. But for now, let's assume this is true, this holds, and what we would get then is this equation here for our covariance matrix. Yeah. So once we uploaded the data, what we get immediately using this formula here, we just have to plug it into Matlab. Yeah, we get immediately the point estimate of our beta, the beta vector. We get also the corresponding covariance matrix, yeah, using this formula and this formula here. So we just have to plug it into Matlab, and it spits us out all what we need. We just have to bring it into the right order then. And let's think we have like 10,000 stocks. So these things become, of course, infeasible if you would do it in eViews, yeah, obviously. So it would take ages. But once you know what's going on, once you know how to calculate these things, then you can easily do it in Matlab and do it for a huge data set. Yeah. But of course, you have to know what's going on. And you have also to know what's going on or what happens if some of the assumption or if the data is not supporting your assumptions, which can have severe consequences, as we have seen last time. Yeah. And that's also something, if you read carefully the research articles, yeah, that are published in sometimes even in decent journals, you know, they don't even discuss these things. They don't even discuss if the assumptions are hold actually for their models. So they sometimes you read research papers, yeah, and you don't even know if what they did actually is reasonable. Yeah, because if you do not test if your model assumptions actually hold, or if they're actually supported by the data, then everything you do could be nonsense. You know, that's the problem. And there are many research papers out there, not only in finance, also in other kind of research like psychology, that are completely nonsense. Yeah. Sorry to say that, but that is true. So always think critically and think about if what you do is reasonable. So now we just use what we know now. We employ what we know now for our model. So can you see that? I don't know. I think it's a little bit unsharp, but yeah. So exercise 3. You consider the CAPM and want to test whether the model holds. Estimate the following models for all stocks. So now we have the excess returns. Yeah. YI, YIT is the gross return of stock I at time t minus the risk-free rate. So what we get on the left-hand side here of the equation are the excess returns of stock I is equal to beta 0. Beta 0 is our alpha. Yeah, it's the intercept. It's the corresponding point estimate for the intercept term, plus beta 1 of S at I, which is the market it's the sensitivity against the market factor, and then times market factor minus RF, so which is what we have in parentheses on the right-hand side is the excess return of the market factor, yeah, plus U, which is the error term of S at I at time t. Yeah, and again in our sample, yeah, you know already what stocks we have, Swedish stocks like Volvo, SSRB, and all this stuff. Market factor, we use the OMIC 30 index, like in the previous exercise. That's nothing new. Yeah, again, parameter beta 1 is the market exposure, the sensitivity against the stock market. Beta 0 is measures the abnormal return, respectively the mispricing, yeah, because it's the systematic part of the error term. That's the way how you can interpret it. As risk-free rate, we use the repo renta, which is the interest rate in Sweden, which was actually negative. Yeah, like so, the real interest rate in the Swedish economy was actually negative. Could be also interesting research question. You know what happens, or what may be the consequences if the real interest rate is negative. We have not seen that earlier in history. It's the first time in history. So what happens if you have money on your bank account, yeah, and the interest rates are negative? You get like 0% on your bank account, and the inflation is like 2%. What happens then with your capital, with your money? Is here any finance student? So you have capital loss. Every year you lose capital. Yeah. So if the inflation is higher than the interest rate that you get, you lose your money. Your purchasing power decreases over time. Yeah. What's with the debt of the government? Yeah, you can think about it at home. Yeah, there may be a reason for why the government keeps low interest rates, or why there are low interest rates. Yeah. Maybe there's a switch in wealth. Yeah, if people have a lot of money on their accounts and their money decreases over time, what does that mean? Yeah. So how do we start here in order to solve this problem? So again, we start by uploading our data. This is nothing new what happens here. X is defined as the, we define X as the first column in our data matrix. Let's move this here away. We need some space here. So again, we have our data matrix, like in the previous lecture. We know this already. And in the first column, we have the gross returns of our index. So in this command, if we say, okay, this is our data matrix here, data, and we know it's 215 by 16 matrix. And if we say, okay, X should be data, double point, comma 1. So it tells Matlab, okay, go to the data matrix here. We know the second guy here denotes the column index. Go to the first column. Double point means take all rows. So X is defined as the whole first column vector. That's it. Like the previous time, nothing new. In the same manner, we define our Y matrix. Y are the gross returns or stocks, and we know already they are located from column 2 to column 15, right? In those columns, we find the gross returns for our stocks. So we define Y as data from like all rows and columns 2 to 15. So then our risk-free rate is the last column here in our data matrix. We know that already. It's the 16th column here. There's the risk-free rate, the repo renta. So let's define RF as the 16th column. So then we know T is 215, or we can define it as length from Y. And there was a student yesterday who had this height comment. Was it height? Or how did you define the length of the vector? Yeah.
Sorry?
You said in your Matlab version you don't have the comment length.
It just says that it doesn't recognize size or what you have there. Length. So I just figured out it would be like height.
Okay, but it recognizes the height as a command.
Yeah.
Okay. Yeah. So
it said that I have to use height, length, weight, or size.
Okay. So in case of doubt, you can just write 215. In case of doubt, you can just write 215. So that doesn't matter. Otherwise, you need to figure out. Matlab is always developed. And there are some new comments coming, and so different versions obviously use different comments, and there are some toolboxes or some not toolboxes but scripts, or was it plugins, different plugins and all this stuff. So otherwise, in case of doubt, you just write what it is, and it's 215 in our case. Of course, you know the data length of your sample. You know that before you upload it. So you can just write 215 if you want. So K is 14 in our case. We have 14 stocks. Let's define K as 14. Then we want to construct our guess return matrix. And what happens here is exactly the same that we did already in the first lecture or in the second lecture. We just subtract the risk-free rate from each corresponding element of the gross returns here. And we construct the Y1 matrix, which contains then our excess returns. X1 should denote the excess return of the market factor. So what we do is same thing like last time or like previous lecture. We subtract the risk-free rate vector from our vector of market returns, simply. Or as we do here, we can do it also in a loop and do it step by step, element by element. It doesn't matter. I told you you can also just write because the vectors have the same dimension, of course, per definition. So we can define the x1 vector simply as x minus rf. That's it. Yeah. And what we would get is the excess returns of the stock index. So what we then do, what is then new here? Constant. We want to have a constant. Let's define constant should be once t by 1, right? Yeah. So this tells us, okay, what we are doing is we construct a vector. We call it constant. That's a vector. And it should have once. This command means, or tells Matlab, give me once, how many, and which dimension you define here in the parentheses. So capital T is 215. So you have one column. So what you want to have is a column vector, one column, and capital T, which is 215, once. So what you get is a vector of 215 once. T by 1. If you want to have a matrix of ones, yeah, a matrix that has, for instance, like 2 vector of ones, like in a matrix, yeah, which is then t by 2, you would write ones and then in parentheses capital T, comma 2. Yeah. If you want to have a row vector instead, a row vector of ones, yeah, you would write ones in parentheses 1, comma t. Then it would give you the same t by 1, the same vector, but as a row vector of ones with t columns, you know. So, but we want to code a column vector of ones because in our regressor matrix X, we operate with columns. In the first column, we have a vector of ones because now we add an intercept term here in our CAPM model, yeah. And the second column is the vector of excess returns. So in our case now, in our empirical example, our X we define as we need a vector of ones as a first column, and in the second column we have the vector of excess returns from the market. So it's a T by 2 matrix. Yeah. But that's our regressor matrix, our factor containing the market factor and the vector of ones. So what we do is actually, so we have already stored the excess return vector, which is x1. So the only thing that we have to do is, okay, we plug in x1, the vector of constants, which we have denoted as constant, and x1. So that's our X matrix. Yeah. You define a matrix in Matlab using this parenthesis here, and then you can write in the vectors that your matrix should contain. In our case, we define our X matrix, our regressor matrix like that. So we have first a vector, this constant vector here of ones, and the second the excess returns of the market vector that we defined earlier. Yeah. So and then we do basically a similar thing that we did earlier. We want to store the point estimates and also the corresponding t statistics. So we construct a beta vector here where we want to store the corresponding point estimates. So we define it as zeros again, like we did last time. Zeros k by 2, or k is 14, so it doesn't matter if you write 14 or k, because we have k defined already earlier. So it's simply it's a matrix that has zeros. And dimension 14 by 2. And now we want to store in this matrix the corresponding estimates for all of our 14 stocks. So what we want to have here, in the first row, the first element, first row, first column, we want to have the corresponding alpha, so like the intercept term of the first stock. The second element here, in the first row, should be the corresponding market sensitivity of the first stock here, this guy here. So then in the second row here, because this is our stock dimension, we want to have the market, intercept term, the corresponding intercept term here of the first stock, and the second element should be the corresponding market sensitivity of the second stock. Yeah? So this is the order how we want to store our results. You can read it already from the dimension. Yeah? So each stock and each row, first column, the intercept term, second column, we want to store the market sensitivities. Yeah? That's the way how it works. That's the way what we want to do. So what's going on here then? So we have now created our zero matrix, our beta matrix consisting of zeros, and now we want to put in the corresponding values, the corresponding point estimates. So we define, again, we operate with a for loop here. Our for loop is from I 1 to k. I is 1 to k. So, and what's going on here? We start with I is 1. What happens then? So beta underscore 1 is equal with, and then we have this expression here. What does that mean? Constant x1 in parentheses times, it's transposed actually, times itself and we have this inverted sign, right? Yeah. This means take what is in parentheses to the power of -1. And this means we have to invert it. As an alternative, you will get the same estimate if you write INV, which means inverse of what is in parentheses. But you can also write it as the formula to the power of -1. Which means also take the inverse, take it to the power of -1, whatever is in parentheses, okay? So, then we continue. We know already if we have these 3 dots, this means just continue the same command in the next row. We have discussed it last time. If you would have more space, we can just continue writing here. So we take again the same expression, constant and x1 in this brackets here, and then take it times y1, and we know in y1 we have the excess returns, double point I. And we said I should be now 1. Okay? I is now 1. So what does that mean? So this means here, this is our y. That's our y. And this means here, from the excess return matrix, go to the first column. You know, this is the column index. and take all rows. So this is it grabs the excess returns of the first stock. In the first column of this Y1 matrix are the excess returns of the first stock. So what is this guy here? This is our excess return matrix, right? This is X. And we have to transpose it, right? Yeah, its name is transposed. So we have to transpose that guy. What we have in brackets here is our X matrix. Huh? It's a vector of 1s and x1. We can also define it. What we could do is we could define X as this matrix here, having constant and x1. We could define it as that, put it outside the loop, outside the for loop, yeah, either before or behind the beta, and then we could replace in this equation this expression here by x or xx, or however we want to define our input matrix, yeah. But that's our regressor matrix. That's X, and we have to take the inverse. We have to take this transpose. So with X prime. So what we have here is the same thing. Prime transpose times itself. This means take the inverse, and it's in parentheses. So it's this guy. And what is that? It's our beta hat. Yeah, x prime x inverted x prime y. It's our simple OLS formula. So what we get is here, in the first iteration, if I is 1, we get our beta estimates. And in this vector here is the beta 0 and the beta 1, the estimated. It's 2 by 1 for the first stock. Yeah, for the first stock. What do we have to do? So this is a 2 by 1 vector, what we get after the first iteration. We have to transpose this guy, make it a 1 by t vector. Yeah, we have to transpose it. It's beta underscore 1. So what we do is we have to transpose it and put it here. Because there, our two elements should be stored, yeah, as we said earlier. So transpose it and put it in there. This is exactly what we see here. So if I is 1, it says put into this position here 1, and double point means take all columns in this case. So I is 1, first row, all columns. So it's the dimension is 1 by 2. So what we put in there should be also 1 by 2, yeah? Because this dimension here is 1 by 2 if I is 1, because there are only 2 columns. So if we we have to transpose this guy here, our beta underscore 1. This is our beta underscore 1 estimate. So we have to transpose it and put it in here. And that's exactly what we do here. We transpose this guy, beta underscore 1 is transposed, and we put it here into the position of our beta vector, into position in the first row and all columns. So if we would have an error here, if we would have misdefined our matrix here, if we would have defined our matrix as, for instance, this beta 0 matrix where we want to store our results as k by 1 matrix, and this guy would have only one vector of zeros here, then Matlab would spit out like an error message that the dimension is wrong. So then we have to go through the code and look, okay, where did we miscode it? And this happens, of course, in the beginning all the time. And then you have to go through the code, and then you have to think, okay, where are the dimensions not matching here? And then you have to figure out what you have done, and so on and so forth. So that's why it's important that you define everything correctly. So if you know here you want to store the corresponding point estimates, and you have two regressors, so then of course the matrix that you construct in order to store your results needs to have the corresponding dimension. So that's important. But these are like beginner mistakes. This happens to everybody. So don't be disencouraged. That happens to me still. So that's no problem. You get better. It's learning by doing, and you get better by repetition. That's always like that, whatever you do. So it's just clear to everybody what's going on here. What this code here is doing. Same thing, but like last time. But last time we had just one parameter to store. So now we have two parameters to store. So our results are now stored in a matrix. It's not a result vector, it's a result matrix. And think about if you would use as a pricing model the Farmer and French 5-factor model, then this guy here needs to be much larger if you want to store all of our results. So then we have to have if you would use in this case Farmer and French 5-factor model, this would be, and add a constant term, then this would be 14 by 6. So we would then have 6 zeros in each row. So this depends on the asset pricing model that you choose. So once we have done that, here I wrote you, if you want to plot, for instance, once you have done this first for loop here, and you have here in your, then you have numbers here in this beta matrix. You have numbers here everywhere, and if you want to see after you implemented this for loop, you want to see actually the distribution of the intercept terms, which is in the first column here of your beta matrix. You could write the comment plot beta colon comma 1. Then it plots you what is in the first column here, which are the intercept estimates. So if you want to see, it could be also that you would like to see, okay, what about your data sample? What about the distribution of the betas? Then you could write, okay, then it's plot in parentheses beta double point comma 1. Then it plots you what is here in the second column. And if you want to have, if you want to see the sorted betas here, if you want to see the sorted betas or the sorted intercept terms from lowest to highest, then you have a first guess about how your data sample looks like, how the distribution looks like. You have a first view. So all of, what you first do if you make an empirical analysis, you get some graphs, in order to get a visual touch of your data sample, because the human brain is mostly visual oriented. Humans are visually oriented in contrast to animals. They are different, but we are most visual creatures, and it's often easy to, if you have graphs, then you know roughly what's going on in your data. So you could also basically, if you want to see the sorted intercept terms, you can just write plot in parentheses sort beta double point 1. So then it would plot you the sorted intercept terms here. It would sort the first column and then plot it. So you can do many different, let's play around a little bit, you can do many things here. So what we do then next? Again, we create a matrix where we want to store our results, but now we want to store the corresponding t-statistics for all of our point estimates, yeah, using the formulas that we just derived in the beginning of the lecture. So I denoted it in this example, t underscore statistics underscore beta equal to zeros, parentheses open, 14,2, parentheses closed. So it has, of course, this matrix here needs to have the same dimension as our matrix where we store the corresponding point estimates. So beta is a zero matrix that has 14 rows and 2 columns, and here also this matrix here where we store the corresponding t-statistics has also 14 rows and 2 columns. Yeah? So and each element should have the corresponding t-statistics for each corresponding element here in our point estimate matrix. Yeah? Otherwise, it would be just too fuzzy. And we have only 9 minutes left, so I would have liked to go through in detail, but let's do it then. You know, we took some more time here for the derivation because it's so important to know what's going on here. Otherwise, this will be, if you don't know these derivations, then this will be like a nightmare here, what happens. But since we have now derived everything in the beginning of the lecture, that's easy peasy. So let's continue then here for with the t-statistics tomorrow. Yeah.